All right, so we introduced this new concept, electric field, last time. And the definition of the electric field is this, right? If there is an electric field created by some source charge, okay, and the electric field is defined as if you bring a test charge in that electric field created by some source charge, okay, and if you imagine the force on this test charge at a single point, at a specific point, divide that force by the charge, the test charge, then it's going to be the electric field, okay? And then, as I said, we are going to find the fundamental theory to calculate the electric field, so that once we have the electric field, calculating the force on any test charge, it's going to be very easy, okay? So this is pretty much like the gravitational force we learn, gravity force we learn, right, in physics 1. Once I have found the gravitational field created by the Earth, okay, in this case it's always 9.8, right, calculating the gravitational force of any object, right, it's going to be super easy. I just multiply the mass by the 9.8 and that's it, right? But of course, I still need a theory to find this little g, this gravitational field created by the Earth, right? Our theory, what is the fundamental theory? The fundamental theory is actually this law discovered by Newton, right? So remember, we use this law to find out the little g on the Earth is 9.8 meters per second squared, which is a constant, almost constant on the surface of the Earth, right? Once you have done this work, okay, you have finished this, you use the fundamental theory to find the gravitational field created by the Earth. You can go ahead and calculate the force every object feels in this gravitational field very, very easily, okay? So that's why we wanted to introduce this new concept, the electric field. And also, as I said, electric field, gravitational field, they do exist, okay? You can't deny their existence because you don't see them, right? You don't see a lot of things, but they exist. Microwaves, right? You don't see microwaves, but you definitely know they exist, okay? They're just the oscillations of the electric field and magnetic field, okay? So electric field does exist, right? So, and then we also introduced electric field lines to help us visualize electric field, right? We don't see them. We can still use some tools to help us visualize them. It's like we draw arrows to help us visualize forces, velocities, accelerations, right, for vectors. For electric field, we also draw arrows, okay, to these, we call them electric field lines to help us visualize electric field, okay? But now we're going to find a fundamental theory. As I said, we still need to find a fundamental theory like this to calculate electric field from any source, right? And then that's going to be the hard part, right? That's not going to be easy, right? But once I have found a theory, I can always use the theory, theoretically calculate the electric field created by any source charge. Then I place a test charge at any point, calculating the force on the test charge, super easy, okay? So that's what we're going to do in this lecture. So we're going to start with single point charge, okay? Single point charge, the easiest, the simplest source charge, okay? Then we're going to generalize it to a group of point charges, and then even a continuous charge distribution, okay? So we're going to still start with this definition and then use Coulomb's law to help us find the theory for the electric field produced by a single point charge. Okay, so let's do that. So let's start with the simplest case, a positive source charge. A positive source charge, right? A positive source charge, as we discussed last time, the electric field lines, we draw electric field lines outward. So the convention is this. We draw electric field lines outward, okay, to present the electric field created by this positive source charge, okay. So then I want to find the electric field at this point. Direction, we already know that. We don't need to worry about direction. Our convention is always this, right? So outward, okay? So away from the test charge, away from the source charge. I'm sorry, source charge, not test charge. Okay, this field is created by the source charge. Okay, so that's the direction. So then I can actually draw the direction of the electric field at any point. Right? For example, what is the direction of the electric field at this point? Okay, well, okay, I can draw it for you. It's going to be away from it. Right? What is the direction of the electric field at this point? Away from it. Right? So that's how I would draw the electric field. So the direction, okay, we already figured it out. Well, it's a convention we use. Now the magnitude. The magnitude, let's use this definition, right? So I would have to bring a task charge. So let's bring a task charge at this point, Q naught, okay? So this guy, I'm not doing anything with this source. I bring a task charge at this point. So I want to find expression for the magnetic electric field at this point, okay, using this definition. So if I want to find the magnitude of the electric field, I would do this. So everything, magnitude, absolute value, okay. Then the electric force from the source charge Q on this test charge Q naught, actually I know how to calculate that. That's the first law we learn and this apart, right? That's just Coulomb's law, right? If you want me to find the force between this the source charge and this test charge, okay, it doesn't matter how you call them. They are two charges to me. If there are two charges, the force between them is always going to be this. Big Q, source charge, R squared. Where R is the distance between them, it's not a radius, okay? So let's put it into this equation. So I would get KE, Q naught over R squared over Q naught. Okay? Now I can cancel this Q naught, right? And everything's positive, right? And in this case, I already made everything positive. You don't need to worry about that. So this Q naught is going to cancel this Q naught. So what do you get at the end? And then that's it. Okay? That is the expression for the electric field at any point created by the source charge, okay? Because K is a constant, Q, well, of course you're going to tell me the source charge if you want me to calculate the source charge, the electric field created by this source charge for you. And you also need to specify the point you want me to calculate electric field, right? For example, if you say, I have a charge here, right, 5 coulombs. I want you to calculate the electric field at this point, which has 20 centimeters from the source charge, okay? Direction easy, away from, radially, outward, okay? Magnitude, plug this 5 coulomb in, plug this 20 centimeters in, I can give you the number, right? And then if you say that, well, what about this point? Okay, well, okay, direction, radially outward, I'm going to draw an arrow in that way. Magnitude, if you tell me this distance is 18 centimeters, okay? 5 coulombs at the top, 18 centimeters at the bottom, boom, I'll give you a number. That's it. That is the theory, right? So it's actually easier than you thought, okay? So that's a theory for point charge, right? So electric field magnitude is always Ke times the source charge divided by the distance squared, okay? So it depends only on the source charge. It doesn't depend on the test charge, right? Even though I use the test charge, okay, a totally arbitrary test charge as a tool to help me derive this theory. But at the end, right, once I found this theory, I don't need to use a test charge to calculate the electric field at any point, right? So I can always do this, okay? And then, of course, for negative charge, the expression is going to be the same because I'm still calculating the magnitude, right? And the direction is just going to be, our convention is that for a negative charge, the electric field is always toward the charge. So if you have a test charge, if you have a source charge here, okay, Q, say like negative 4 coulombs, okay. Now if you ask me, find the electric field created by this negative source at this point. Okay, how do I find that? Direction easy, radially inward. So I would draw an arrow. Okay, you don't have to draw this arrow, until the source charge, right? You just need to tell me the direction. Okay. So I would say that's the direction of the electric field at that point, right? Always radial inward toward the source charge because this is a negative source. Then, what about magnitude? Magnitude easy. Okay, what is the distance? Okay, say this distance is 25 centimeters. I would put 4 coulombs at the top, right? It's negative, but this absolute sign is going to make it positive. I'm going to put 0.25 meters at the bottom, square that, and then that's going to be the number. Okay, so I know the electric field at this point. So if you pick a different point, like okay, what about this point? Okay, direction, I draw it for you, radial inward, okay, toward the charge. That's the direction of the electric field at that point. What about the magnitude? Okay, what is the distance from the source charge to this point? If this is 8 centimeters, okay, good. 4 coulombs at the top, okay, make this positive. 0.08 meters at the bottom. Put these 3 numbers in the calculator. Okay, I will give you the number. I will tell you the magnitude of the electric field at this point. So that's going to be the theory for any point charge as the source, right? I'm done. I already found the theory. If you ask me to find the electric field at every single point, okay, it's going to take me some time, okay, to find out a lot of time. If you want me to find like a 1,000, you pick 1,000 points, but the theory is always this, right? All I need to do is just tell you, this is the theory. Go ahead, use this theory. If you want to find the electric field at any point, okay, then you're on your own, okay? It's like if I tell you the gravity of anything, it's always the mass times 9.8. Go ahead, use this theory, okay? You can use that to calculate the force on every single, the gravitational force on every single mass, okay? I only need to tell you the theory, okay? Then you can apply the theory to any case you like, okay? So we have found the theory, okay? So direction depends on the sign of the source charge, right? Positive, you draw a direction, you draw an arrow toward the charge, away from the charge. If the source charge is positive, okay? Radial outward. If it's a negative charge, you draw an arrow toward the charge, radial inward, okay? Magnitude, always this equation. All you need is the source charge and the distance from the source charge to the point you want to calculate the electric field. Okay, we're done. That's a theory for point charge. So sometimes you see a notation like this. Okay, if you read different books, okay, some books they will write this vector equation for the electric field. Okay, so it's the equation on slide 7. They would do this. Okay, or big Q, doesn't matter. Okay, big Q, little q, doesn't matter. They will put expression like this and then multiply it by in front of this r hat vector. So this is a vector. This is a unit vector in the radial direction. Okay, so for example, if you have a charge, okay, the r hat at this point is just going to be in this direction. Okay, the unit vector, so the magnitude of this guy is always 1. Okay, so it's pretty much like this I hat, J hat, K hat we have been using. It's just a notation. Okay, this guy just tells you literally in the radial direction. Okay, so that's why this equation is going to have all the information, right? Both the magnitude and the direction, right? The magnitude, you just take the magnitude of everything, right? This magnitude is 1, so you don't need to worry about it. And the magnitude of this thing is just going to give you this equation, right? Direction, this Q, you see that there's no absolute sign. So if this is positive, it's going to be radial outward. If it's negative, you have a negative sign in front of this unit vector in radial direction, it's going to reverse its direction, okay? So physicists always want to write things, okay, everything in a very nice equation. They want to include as much information as possible. So that's why you see a lot of books, they would use this equation. But what this means is literally the magnitude and the direction I wrote on slide 7. It's just telling you magnitude is this, direction, it's always going to be radiated outward for a positive source, radiated inward for a negative source, right? So that's just a nice notation. But what this means, what this equation, nice equation means, is just what we learn, right? That's just a nice notation. So all the physicists, when they see this equation, they know what it means, right? So don't be scared by these notations, right? When I say a vector A is 4I hat plus 5J hat, right? If you don't know what I hat and J hat mean, you will figure out, right? But what I hat and J hat mean are literally 4 in X direction and 5 in Y direction, right? When you see this, when physicists see this notation, they know that's what it means, right? It's because we don't want to write, a lot of words. We use symbols, okay? So this is a nice equation, but again, when I use this theory, I still do that in 2 steps, right? Magnitude and direction, magnitude and direction, okay? Now, okay, sometimes people are gonna confuse this theory we just learned with this equation we rearranged, okay, last time, okay? Because there's always like the direction, okay? The direction is always going to depend on the sign of the charge, so they get confused, okay? That's why I summarized everything we have discussed in 2 different theories on slide 8. So take a look at that. This is the first theory, okay, we're going to use to calculate the electric field produced by any source charge, okay? I give you a source charge like this. I want you to calculate the electric field at any point produced by the source charge, okay? So you're going to use this equation to find the magnitude, and then you're going to use our convention to draw these arrows, right, away from a positive charge toward the source charge when the charge is negative, okay? That's one theory. That's the theory you use when you calculate the electric field produced by source charge, okay? Then once you have the electric field, you use that theory to calculate the electric field created by source charge. You can go ahead and use this, rearrange the equation to find the force, okay? So you can think of it as a different theory, okay? If I already have the electric field created by some source, at this point, say in this direction, electric field equals 5 newtons per coulomb. I already did that. I already used the fundamental theory to calculate electric field. It may took me like half an hour to do that, but I'm just going to tell you, I already did that. Don't worry about it. There is an electric field created by some source. You don't need to worry about it. The magnitude is 5 newtons per coulomb. Direction is in that direction. And then, if I bring different test charge to this point, how do you calculate the electric force on it? Okay, say I place a test charge, right? 3 coulombs here. I want you to find the force on this guy. That's when you use this rearrange the equation. The force is always going to be equal to the test charge times E. And then how do I use this to rearrange the equation? I would again do it in 2 steps. The magnitude is going to be this. The product of this test charge and the electric field, both positive, make them positive because you just need the magnitude. And the direction, you're going to take a look at the sign of the test charge. Right now you don't have the source charge. I don't even need you to worry about the source charge. I'm just going to tell you there is an electric field at this point. So you take a look at the sign of the test charge. That's going to help you figure out the direction of the force. Okay? And the force only has two options, right? It's going to be the same as the electric field. If the test charge is positive, it's going to be opposite to the electric field if the test charge is negative. Okay? So that means if you tell me the electric field at this point is 5 newtons per coulomb in that direction, and you place a 3 coulomb charge, test charge here, you want me to find a force for you, I would say force, multiply them together, 15 newtons. Direction, because this is a positive test charge, I would draw the direction the same as this electric field, okay? That's how you use this, rearrange the equation to calculate force on a test charge when the electric field has already been calculated either by you or some people, okay? You don't need to worry about it anymore, okay? So that's the easy part, okay? But still you should be careful because the test charge can also be positive or negative. Then if this is the same electric field, right? Okay, I already calculated the electric field, okay? 5 newtons per coulomb at this point. I don't want you to worry about the detail. I just tell you there's the electric field at this point, 5 newtons per coulomb. Now I'm going to bring a negative charge, say negative 4 coulombs here, okay? I want you to calculate. Remember, this electric field is not created by this guy, right? It's produced by some source charge. I don't want you to worry about it. I already did the hard work, okay? 5 newtons per coulomb created by some source charge, okay? Now I want you to find the force on this negative 4 nanocoulomb charge at the same point, right? I bring these two different charges at the same point. I want you to show me the force. So, okay, so you would still use this theory, right? The force, multiply these two numbers together, both positive. So the force, I'm going to tell you, is going to be 20 newtons. So this Q naught is going to feel a 20 Newton force. What is the direction? Take a look at the sign of this test charge. Okay, the test charge is negative. So the force, it's going to be opposite to the field, okay? So that's how you calculate the force once you already have the field, okay? You still need to take a look at the sign of the test charge to figure out the direction of the force. And the magnitude, you just multiply the force, the electric field and the test charge together, magnitude, okay? This theory is for electric field produced by source charge, right? That's the first step. That's actually harder than that one. You would have to use this theory, okay? And then to find the magnitude of the electric field at any point. And then you take a look at the sign of the source charge. You know how to draw the electric field, okay? In this case, it's going to be away or toward the charge, okay? So it's a little bit different than that, okay? Don't confuse them with the other, all right? So again, it's always easier to understand the theory in a real problem with real numbers. So that's what we're going to do next, okay? Now let's take a look at the question on slide 9. So now we're going to use these two theories, okay, to find the force from two charges on one charge. Okay, so let's do that. So our goal is this. I still want to calculate the force, okay, from this 6 nanocoulomb charge and this negative 3 nanocoulomb charge on this 5 nanocoulomb charge at the origin, right? You can do this using Coulomb's law, right? You can say that this is Q1, Q2, Q3, right? I'm just going to calculate the force from Q1 on Q3, right? Draw that arrow using Coulomb's law, find the magnitude. I'm going to find the force from Q2 on Q3, okay? And then draw that arrow, use Coulomb's law to find the magnitude, and then you will have two forces, right? Two vectors, you break them into x and y, combine x components, y components, then you combine them to find a net force, both magnitude and direction, okay? So now we're gonna do that in a different way. We're gonna use this field concept to find the force on this guy. So we're gonna view it in a different way, okay? So what we are gonna do is that we're gonna treat these two guys as the source, okay? So now I have two sources. These two source charges, they're gonna produce electric field right at this origin, okay? And then this charge, 5 nanocoulomb charge, is the test charge you bring in to that point. So this 5 nanocoulomb charge feels that it's inside a field. So it's gonna feel a force on it, right? It doesn't even know if this Q1 and Q2 exist. It doesn't. It just feels that I'm in an electric field, right? I feel force. It's like I'm in the gravitational field created by the Earth. Even if I don't know it is from the Earth, I still feel that there's a gravity on me down, right? It comes from something, that's fine, I don't care, but I can always find a force as long as I already have the gravitational field 9.8, okay? So that's what we're gonna do. We're gonna do that in 2 steps, okay? So on slide 9, we're gonna find the electric field produced by these 2 sources at the origin using this theory we just derived. So now I can totally forget about this test charge at the origin. So let's redraw these 2 charges, okay? So I'm going to call this guy Q1, 6 nanocoulombs. This guy Q2, -3 nanocoulombs, okay? Now this guy and this guy, they will produce electric field at this point, okay? So now you have 2 electric fields at the same point, so you will get a net electric field, right? Because there's still 2 vectors at the same location, you will get a net vector. So that's what we're going to do on slide 9. Now, okay, so let's first find the electric field created by this guy, okay? So I'm going to use the theory we just learned. The magnitude, easy. If I call it E1, that's going to be KE Q1 absolute value R1 squared. Okay, do I know all these numbers? Q1, yes, put it in. What is R1? R1 has a definition. Everything has a definition in physics. If you want to find that, just use the definition. The definition is this. The R is the distance from the source charge to the point you want to calculate electric field. This is the source charge. I want to calculate the electric field at this point. Oh, so this is the R1 I'm going to use. And what is this R1? The problem already tells you, right? This is 0.3 meters. Okay, so that's the R1, Q1 I plug in. You see that I can find this number. But this is a vector, right? You should find the direction as well. What is the direction? Okay, what is our convention? If it's a positive source charge, the electric field is always radially outward, okay, away from the charge. So I would draw an arrow away from it. That's how I draw E1. Okay? So that's how I'm going to draw E1. All right? So you see, now I know everything about the electric field produced by this Q1 at this point. Okay? Now, this guy is also here. This guy is also a source charge. So this guy also produces an electric field at this point. How do I find that electric field created by this guy? I use the same theory, right? Because it's just a different source charge. The theory is still the same. Now E2, okay, KE Q2 over R2 squared. Now do I have all the numbers? Q2, yes. Put it in, make it positive because I have absolute value sign here. R2, what is the definition of R2? The distance from the source charge Q2 to the point you want to calculate the electric field. This is the source charge. I want to calculate electric field at the origin. So this is going to be R2 I plug in. What is this number? Oh, the problem already tells us that number. 0.1 meter. Okay, you see that now I have all the numbers I need for this electric field. Put them in, you will get this number. Okay, What is the direction? Okay, the direction is this. What is our convention? Negative source charge, the electric field is always radially inward. So you draw an arrow toward this charge. Okay, so that's going to be E2. So if that's E2, then you see that how do I find the net electric field? Okay, now you can forget about are they electric field, electric force, or gravity force, or normal force, or velocity, or acceleration. It doesn't matter. You have two vectors. You want to add these two vectors. You just do vector analysis, right? How do you add two vectors? You break them into x and y components. You add components together. You only add x components together. You add y components together, right? And then you combine these x and y components to find the net vector, both the magnitude and direction. That's how you combine, how you add two vectors, right? So that theory never changes, right? Doesn't matter what this vector is called. Now this vector is electric field. Fine. Find xy components of this guy. Find xy components of this guy, then work with the components. Well, this question, okay, it's a little easier because I already have E1 totally in x direction, well, negative x direction. I have E2 totally on y, negative y axis, so I don't need to break them. I already have them as xy components. Then how do you combine them to find the net electric field? Well, that's easy. I know how to draw that pictorially, right? That's gonna be the electric field, net electric field. All right, so now you see that all I need to do is just find these two numbers and then use trig to find the magnitude of this net electric field by doing x squared plus y squared and square root, right? Direction, we usually just specify the direction using a reference axis and angle, right? So in this case, why don't we just say, pick this angle, theta, so that's going to be the angle below negative x-axis, right? All right, so now, and then because you already have the x and y components, you already have a right triangle, you can go ahead and plug numbers in to find this, the magnitude and the direction of this net electric field. Okay, now you can pause the video and then do the algebra. All right, so let's see, what is this number I got? You put all the numbers in, convert everything into SI units. Net coulomb is 10 to the negative 9 coulombs. Okay, you put all the numbers in. Don't forget the square, okay? That's a common mistake people make. You get 600 newtons per coulomb, okay? You put all the numbers in for E2, I got this. 2,700 newtons per coulomb. Now we can combine them. They're already x and y components, right? So the E net from this diagram, you draw this diagram, you know what to do, right? You don't need to remember a lot of conclusions. Well, it's just going to be EX squared, x squared plus y squared. In this case, it's just going to be E1 squared plus E2 squared and the square root. That's going to give me 2,766 newtons per coulomb. So that's the magnitude of this net electric field. What about the direction? Okay, if I decide to use this angle, theta, that's going to be tangent inverse E2 over E1. Right? Okay, so because opposite over adjacent. Okay, so this number is going to be 77.5 degrees. Okay, so that's the first part. I found so it's going to be this angle below negative x axis. That's how I would describe the direction, right? Okay, of course, if you like, you can use this angle, right? Say this angle is alpha. You find this alpha angle, you can say it has an alpha angle with this negative y-axis, right? So I also know what you mean, okay? Now we have finished this part. So this is actually the hard part. You need to use this theory to find the electric field created by each source charge and then add them as vectors. then that's going to be the net electric field at that point. Now, if I bring a task charge at this point, only at this point, right? Because I just find the electric field at this point, okay? Of course, if you want to find the electric field here, you can do that, right? You can definitely do that, okay? But we're just going to use this point as an example. Then I put a task charge here. I want you to find the force. I'm going to use this theory, right? So all I need to do is this. Now I have already found the electric field, okay? So the net electric field created by these two sources, 2766 newtons per coulomb, okay? The angle 77.5 degrees. Now I can totally forget about these two sources, right? I already need, the only information I need is the electric field at this point, okay? Now you bring any task charge to this point. I can find the force for you very easily using this theory, right? So now you bring a 5 nanocoulomb charge, okay? So that's Q naught, that's a task charge. And then you want me to find the force on this guy, okay, easy. Magnitude Q naught times the net electric field I just found. That's going to be the magnitude, right? Direction, what is the sign of the task charge you bring in? Positive. That's this, okay? So now you can pause the video, find the force on this 5 nanocoulomb charge, right? So the number I found is this, okay? You multiply these two numbers together, 1.38 times 10 to the negative 5th newtons. Okay, so this guy feels the force with this value. What is the direction? Well, because the source, the task charge is positive, so the force is going to be in the same direction as the electric field. That's the force field, right? You see that this part is the easy part. Once I have done the hard part, once I have found the electric field created by the source, and the source can be like many charges, right? It doesn't have to be like only 2. Maybe you have 1,000 charges, right? That's fine. I will do the hard work. But once I have done the hard work, this step, it's easy. That's the point, right? Once we have found the fundamental theory to calculate electric field, okay, finding the force, it's going to be very easy. So this guy is pretty much like the 9.8 we already found, okay? And then it's going to be a lot easier if you switch, if you put different charges here. So you don't have to repeat the same process in the first part, right? So take a look at the question on slide 11. If you replace this 5 nanocoulomb charge at the origin with a negative 8 nanocoulomb charge, what is the magnitude and direction of the net electric force on this negative 8 nanocoulomb charge? I'm not doing anything with these two sources, right? So I still don't need to draw them. Now you see the advantage of this concept, electric field. If I replace this charge with a negative 8 nanocoulomb charge, and then if you tell me you still want to do that using Coulomb's law, you're going to do this, right? You're going to place these 3 charges again here, 3 nanocoulomb charge, 6 nanocoulomb, negative 8 nanocoulomb. If you want to use Coulomb's law, find the force from this guy on this guy, right? Vector, okay, magnitude and direction. Find the force from this guy on this guy, right? And then magnitude and direction. And then combine them as vectors, find the magnitude and the direction of the net force. So pretty much, if you want to use Coulomb's law to find the force, okay, pretty much every time I replace this guy with a different charge, you have to repeat the same calculations, right? The same amount of time, right? You're not going to save any time, right? But if I use the field concept, I don't do anything with these 2 charges, right? That's just an example to help you understand the idea, okay? I don't need to draw these 2 sources again, right? All I need to draw is this, okay? The electric field at this point is still the same. Nothing has changed because I'm not doing anything to the source charge, right? Electric field, net electric field at this point is 2766 newtons per coulomb, okay? Nothing has changed. You place another test charge here, Q naught, negative 8 nanocoulomb charge here. Okay, I can find the force for you. I don't need to repeat that, right? I already done hard work. The force on this charge is going to be Q naught times this electric field created by these source charges. Multiply them together, both positive. Direction, again, take a look at the sign of this test charge, okay? And then it's going to be, it only has two options, either the same with the electric field or opposite to the electric field, right? So if you put all the numbers in, what do you get? This guy, you will get 2.21 times 10 to the negative 5th newtons. Okay, so this guy is going to feel that force. What about the direction? Okay, it's a negative source charge. The force is going to be opposite to the direction of the field. So that's how I'm going to draw the force for you, opposite. Okay, so obviously it's going to make an angle 7.5 degrees with positive x-axis, right? So see that now I can save a lot of time if I already found the electric field at this point, right? So I can calculate the force on any test charge very easily, okay? Just one step I can do that. I don't need to repeat this theory, the hard work. So that's the idea. That's why we introduced this concept, electric field. It can definitely help us simplify, okay, the calculations of the electric force, okay. Of course, you still cannot avoid the hard work to calculate the electric field. But once you have found the electric field, pretty much like this 9.8 on the Earth, right? Calculating the force on any test charge, it's going to be very easy, okay? So I'm going to stop here for this lecture.